Vinny.
Hi, sir.
How are you?
I'm fine.
All ready?
Wait, sir.
What do you do in the morning? What do you do in the morning? How's your morning?
Okay.
Okay. You've not anything to say to me before we start, or anything to ask?
No.
Okay, let's start a new topic then. As I say, you have to make an effort to try the question. Right? There's no such thing as learning only. Coming for tuition won't help you unless you make an effort to learn. Okay, same with physics and maths. You cannot study one because there's too many formulas. You don't know which formula to use.
Yeah.
Only by learning to use it, then it becomes part of you. What you are doing is either hit or miss only. That means if the examiner set the right question, you will pass. If not, you will fail. Simple as that. That's not the right way to study. That's what I did in my my undergraduate also. No time to study. So no time to do homework. So just a few weeks before the exam, study. So how to expect to do well? Just hit or miss. Okay, let's go to wave optics 23. Still got 2 more topics. Right? Summarize for you what we are going to study, all the picture there. We start with Huygens principle, which we are studying in the STPM, and interference. Right? Here's the interference. And we specifically study two slit interference pattern on there. And thin film. Right? May look like a reflection and reflection. And diffraction of single slit, this one. Diffraction of grating, this one, grating. Right? That's what we will see using laser. Wave optics, polarization, this is polarization. Where we restrict the wave to vibrate only in one direction. And optical wave.
Teacher, your slide I can't see.
Oh, sorry, you should have told me earlier. Okay, so this all summarized for you. Huygens principle, that one. Interference, that one there. Two slit interference pattern. There's a thin film. Diffraction by single slit, diffraction by grating. Then polarization, where we restrict the waveform to one direction of vibration. Then optical waveguide, there's optical waveguide, where we restrict the wave to in a particular tube there, so they move in one direction. Okay, Huygens principle in your book, page 153. Okay, what are we going to study? You're supposed to know how to state Huygens principle. Use of Huygens principle to explain interference and diffraction phenomenon. Light can behave as wave.
New chapter, right, sir?
Say again.
New chapter, right?
Yeah. New topic, new chapter. 23. Light can behave as wave or particle. 22 we have completed. Then Newton believed that light travel in the form of particles, which he named corpuscles. Particle nature of light was supported by Einstein in his quantum theory. Thomas Young double slit experiment on interference of light also provide evidence of wave nature of light. Huygens came up with Huygens principle to explain the interference of light. Okay, so that maybe just summarize for you what we are going to do. Okay, let's just review what you have studied in your SPM. Each wave class acts like a convex lens and concentrate the light into the screen below the bright line. Okay, so that is this is usually your tray for ripple tank experiment, where the wave is moving along, and then below is your screen. Your light is shining from the top there. So for those direct one, there's a perpendicular surface that goes straight through. Right? Where it's at an angle, there's your plane surface there. Your normal is here. So instead of it going straight through, it's bent towards the normal because the water is higher reflective index. So it concentrated to a bright band here. That's why we see a band. Or we call it a wavefront. Pattern on the screen shows the wave crust for a point source of light. That's a point source of light at the center there. The wavefront spread out as spherical. Spherical if it's 3 dimension. Circular if it's 2 dimension. Right? So there's a representation of your circular wave. Source to the center there. There's the ray. The circle is your wavefront. Right? Center is a point source here in this case. Okay, so this just summarize for you why we see bright and dark band on the screen below here in the ripple tank experiment. Okay, let's summarize for you that the ray shows where the wavefront is moving, direction of propagation of light. This is your wavefront, right? Where the wave is moving. Wavefront are lines or planes that join points vibrating in phase. Well, if you want, you can start writing it down for your worksheet. Worksheet 23, I've sent it to you on Saturday. Yeah, that's your first question. That's the first one that you need to remember. Rays are lines perpendicular to the wavefront, showing the direction of travel of wave. Right? So the ray shows where the wave is moving. This is spherical. If it's 3 dimension. If it's 2 dimension, it's circular waves. Right? So that is your first answer for your worksheet number 1. So have you downloaded or not?
Not yet.
That's why I say you're not making an effort to study. Give you on
Sir,
Saturday.
can you go from the first page, please?
Say again.
No, go to the first slide teacher, again, please.
You're not making an effort to study. That's why you're going to have trouble.
Behind one more slide, sir. No, behind, not in front. In front too.
This is in your book. Nothing new.
Okay, next slide, teacher. Okay, wait, teacher. Each wave crest acts like the convex lens and concentrates the light onto the screen below as bright line.
This is your
Pattern on the
convex
screen. Pattern on the screen shows the wave crest for the point source of light. The wave front spread out as spherical circular waves. Center is the point source.
lens. This all refer to here. These two refer to this diagram. This is your convex lens here. So there's parallel ray of light coming down. The lens converges to the point here. That's all.
So concave means diverge.
Yeah, we're not worried about concave here. We are only converging lens here.
Okay, each wave crest. Okay.
Yeah, it show you the same thing. That's all. Show you why we see when you do the experiment, we see dark line, dark band, and bright band. That's all.
Wait. Sorry. Okay, I just want to understand this. So, why I observe bright and dark line? That means the light will pass through the glass, right? Correct, right?
This is the wave moving. There's a light,
Okay.
parallel rays of light coming through. So this part, like a converging lens, converge it. So you see bright line there. Because of your eye, right? If it's a little bit of dark, little bit of bright, you will call it a dark. That's why you see you won't see a dark line there. You see a dark band there. That's all.
Oh.
Okay.
Okay. Wait, repeat that again. Just sorry, the sentence.
We will come to that later
understand.
on under Young's modulus. Because of your threshold of vision, you will see a little bit a light. You call it dark. Your eye will interpret as dark as well.
Oh,
So you will see as
okay.
a dark line, but you see as dark band.
Yeah, 1 minute. Okay.
Right? So normally we prefer to draw wavefront rather than draw the wave. You can see that this is not drawn properly, right? Distorted. So we just draw wavefront. We just join the crust together, with a single line, then represent it as that. And this arrow, direction of propagation of the wave, we call it the ray. Just draw the ray. Right? Or if you want to draw 3 dimension, there's your 3 dimension. Between the wavefront is your wavelength. Right? So that's your wavefront. That's your ray.
Oh, wavefront, the lines lah.
Yeah, that's your wavefront. This can be a plane. If it's 2 dimension, it can be a plane. If 3 dimension, it can be a plane, but if it's 2 dimension, it can be a line. Okay, it's just various way of drawing your wavefront. Right? Rather than draw the wave, we just draw a vertical line there, and this is your wavefront. Okay, so this is just to review your experiment, your ripple tank. There's your vibrator, there's your lamp, and there's your water. There's your screen, piece of paper on the floor, and that's what you see. As this one vibrate, the wave will move along because the wave is moving on here. Right? The lines will move along. So this vibrator, right? As it vibrates, this plane dipper will move up and down. That's why you see the lines there on the water here.
Which water surface is there, okay? Then below one is the some kind of cardboard, is it?
This is just a piece of paper, a white paper, that's all. To have you to see
Or to show the reflection.
To show the transmission of light, that's all.
Yeah, it's interpreting it. Yep.
So we call
because
it
the
a
water
screen.
is above.
Call it a screen, that's all.
Oh, the white screen. It's showing the pattern lah, by the water surface.
Showing the water pattern. If you have a straight edge. So these are all taken from internet. So internet is good, it's free, but always remember there can be mistake like here. It's not a rod. Right? It show you a spherical object. So it should be called a spherical dipper, not a rod dipper. Okay, this one will all vibrate up and down, and then you form the wave going out from this. This is your center, the center of the source. Right? Huygens principle. Assume light travel in the form of waves. A point light source emits spherical waves. Right? That's your point. Giving out waves. Right? There's a point light source. Give out spherical wave. 2 dimension, we draw a circle. So that's your spherical wavefront. Surface of the sphere is known as the wavefront. So this is your wavefront. Wavefront join point vibrating in phase. So all the points on this surface are all vibrating in phase. That's what it means by wavefront. Then we have the ray showing where the wavefront is moving. It's moving outwards there to the right, up to the left. Right? So light ray is normal. Right? Light ray is normal to the wavefront. Give direction of travel of the wavefront. Right? We just draw some of them. There's still some going to the slanting direction. Right? Or northeast, northwest, southeast, southwest there. Right? It's basically a geometry. It's based on geometry construction, Huygens principle, to determine the new position of wavefront. So this is your wavefront. Right? Initially, how to draw the next wavefront? It's also known as Huygens construction. Right? So each point on the wavefront there, you can consider as a point source. So the point source will emit spherical wave. Right? All the point source there. I'm drawing some of them. There are still some around here. Some around here. I'm drawing some of them. This show you the radius. The radius is ct. C is the speed of light. T is the time. Right? That's the radius. You draw the circle there, or the hemisphere. Right? There's another one here. So the new wavefront, you just draw another sphere touching the surface here. So that's your new wavefront. Right? And then you can repeat the process, draw others. Right? That's for your point source. Right? Same. If you have a plane wavefront, a straight line, at time t equals 0, c is the speed of light, x is the radius or the distance travel during that time, t. So that's your Huygens principle. States that points on a wavefront emit in phase spherical wavelet that travel in the forward direction. So after a time t, the new wavefront is the surface that touches all the wavelets. O is the point that acts at the center of the wavefront. So just take a point there, consider as O. Right? There's a lot of points here. All the O's there. Then that's your distance travel. Just use construction, draw the circle, right, a hemisphere. So that's your point, act as center. Right? And the distance travel is ct. Same. There's a lot of them. I'm just drawing a few of them only. There's another one. O here. Then draw the wavelet, the sphere, and others draw a sphere. And then to find a new wavefront, you just draw a tangent that touches the surface here. So there's a new wavefront. After a certain time t. Okay. Why it's not? You have to memorize what is Huygens principle. Okay, anything to ask?
Where are teacher?
That's your number 2. Right, they're all in phase. Right, they're all in phase. They emit this wavelet, wavelet, wavelet. How to draw a wavelet? You draw it as use a construction, use a compass as a center. Draw the semicircle, semicircle, semicircle. And then the new wavefront is just tangent to the semicircle, that's all.
Wavefront, okay, t equals to 0, then speed of light x equals to ct, states that points on a wavefront emit in phase spherical wavelets that travel in the forward direction. After a time t, the new wavefront is the of the wavelet. Wavelet mean the new wavefront lah, right?
This is a wavelet. This is a wavelet.
Oh.
This is a wavelet. This is a wavelet.
Oh, after the time t equal, after it touches the new t and then
That become a point
touches
source.
the wavelet.
That center
Yeah,
become a
point
point source now. So that's your
Yes,
new
yes.
wavelet. That's your
Ah.
point source. There's a new wavelet. There's a point source.
Point
There's
source
a
new wavelet. Oh. Okay, understood. That means it's traveling lah from one wavefront to another. That's the meaning.
Yeah,
right?
it's traveling just like here. Right? You just draw the wavelet, draw a tangent, and draw the wavelet, draw a tangent, and keep on doing it. That's all. That's how you get your wavefront moving as a straight line. Right? Your plane wave passing through a slit. Then you have your this is your diffraction. That's how it is. It won't go as plane wave, but it will diffract slightly. It will spread out, right, into this region of shadow. This is called a region of shadow. Why is called a region of shadow? So it will spread out. It won't go as straight like that. Right? It will spread out slightly. That's what you see. So this is the diffraction. There you got your plane wave coming from the left hand side here. There's your plane wave. Right? There's your slit. A, slit size, slit width. Okay, so we have completed that. Main thing is Huygens principle. Now what is wavefront? Okay, interference, page 154. Explain the concept of coherence. Explain the concept of optical path difference. Solve related problem. State the condition for constructive and destructive interference. Okay. Interference. Wave can spread out. Right? We call diffraction at narrow aperture. What happens when two or more waves meet? So that's the point source. There's a source here. Center there. Right? There's a disturbance there. So the wave start to move out. There's a spherical wave. So we are interested. This is called interference, where the wave meet. The other center there. Right? The other place there. Or this is the same thing. Right? Two person fishing, throw their fishing line into there, the hook there. It causes the wave to move out.
That means it causes a disruption lah.
So interference is what we observe where the two waves interfere.
Collide.
The two waves meet. Right? So the first thing is coherent. What is coherent? It's constant phase difference between the wave. How to draw it? Coherent light waves. Right? Anytime you look, the cross is the same. The cross is the same place. Cross is the same place for all the wave. Coherent waves are locked together in space and time. Right? So either you look at this is the displacement, this is your time, or displacement distance graph. Lock means it's the same, always the same. They are looked together. The graphs always together. Right? So necessary for them to be coherent is same wavelength. All of them must have the same wavelength or same frequency. Same thing, either same wavelength or same frequency.
For it to be coherent.
Frequency all must be the same, or wavelength must all be the same. Right?
For it to be coherent lah, sir.
Incoherent have no relationship to each other. Like here, right? They are all different wavelength. They may start as coherent, all at the maximum here, or all at minimum there, but because of different wavelength, they won't coincide anymore. Right? If you draw a line there, you won't see them coincide anymore.
Only when same wavelength then yeah lah.
Yep, only when they are same wavelength.
Oh.
Okay, can look at the time there. It doesn't coincide. Okay, it may coincide here. That's all. Different wavelength, you may all start at the same point. That's all. It will coincide. Okay, you look further, it will not coincide anymore. You can see that they are out of phase already. So there is no more coherent already. So necessity, they must have the same wavelength or same frequency. Okay. Condition for coherent, the two waves are, if the two waves are not perfectly monochromatic, means not of identical wavelength, different wavelength, then they will not remain coherent. If the wave is moving with respect to each other, even though they have identical wavelength, they cannot remain coherent. Right? That means they must have the same speed. Right? Like here, the other condition is they must be parallel to each other. These two have the same wavelength, but this one is moving at an angle, different direction to this one. So same wavelength, different direction. So what are the conditions? Same direction and same wavelength. Same speed or velocity. Okay, same direction as this one. Same speed. The different speed, they will move relative to each other, the cross. Okay. Memory work. These are the conditions for coherent. Right? There's your worksheet number 4. You have to make an effort, strictly. You are going to study, if not, you are wasting your money, tuition. Supposed to ask you to write down. Because you're lazy to do homework, ask you to write down.
I can see your slide.
You should have told me when you cannot see it, not keep quiet. Right? Coherent, as I say, you draw at any time or any distance. You look at a cross or look at any point, they must be the same cross, same time. Incoherent, they have different wavelength, will be incoherent. You can start at the same point, right? All of them start at the same point, minimum. But if you look later on, they have the crust, and crust doesn't coincide anymore, right? Only coincide at the initially same. Any other time they are all at different position, different phase. Right? So different wavelength cannot, they won't coincide, they will coincide initially. After you look at a certain time or certain distance, it won't coincide anymore. Or if different direction, they may coincide initially. At a certain distance or certain time, they won't coincide anymore. So that is your condition for being coherent. Same direction and wavelength, same speed. Right here, same wavelength, same speed. So they won't, the crust will move relative to each other. Crust will always be the same crust at any other time. Okay. Here's your worksheet number 4.
Where are teacher? Wait. Different wavelength, same wavelength, but different direction. Okay, if two waves are not perfectly monochromatic, means not of identical, then they will not remain coherent means need to have same wavelength, same wavefront. So, and then same direction. If wave moving with respect to each other, even though they have identical wavelength. Which what that second point is trying to tell, I don't understand.
What second point?
If the wave is moving with respect to each other, even though they have identical wavelength, they already say what they got same wavelength. What? Isn't it coherent?
If the wave is moving with respect to each other, even though they have the same identical wavelength, they cannot remain coherent. That means if I look at this crust, they may have the same, like these two, they may have the same wavelength. But if they have different speed, this crust and this crust are not going to move at the same rate like here. Right? They are going to move with respect to each other, so they won't be coherent anymore.
Oh, okay. Got it.
The crust and crust will not coincide anymore at any other time. Okay.
Okay. Can
Refractive index of medium is defined as the ratio of speed c of light in vacuum to the speed of light in the medium. Right? You can write in formula form c divided by v, and all because c is greater than v, the refractive index is always greater than 1. Refractive index of air, refractive index in air or vacuum is the same. It's about 1.00. And then c, speed of light, is your frequency times wavelength. This is what we'll be using throughout this chapter. Right? Lambda is wavelength in vacuum. So if you have this part is air, this part is your another medium. Right? Maybe you can write it down. Okay, this part is air. The wave travel in air. Then after that, it enter a medium. Or refractive index greater than 1. Okay, That's your wavelength in air. That's your wavelength in the medium. Right? There's from your STPM, the wavelength becomes smaller in the medium. Frequency in vacuum and medium is the same. Frequency doesn't change, right? Whether in air or in the medium is the same. Only the wavelength changes. So wavelength in medium becomes shorter, right? Shorter wavelength. So reflective index you can also show there is a wavelength in air over wavelength in the medium. Okay.
Okay. Teacher, can I have the 5 minutes break, teacher?
You have 5 minutes break, you have to start again. So you want that way, then we start over, we start again, no? Okay, I will stop it.
Okay.
Okay, you see in 5 minutes time then.